Welcome all of you for this class on sediment transports in rivers. As we discussed in the last class, we talk about bed load, we talk about flow resistance in alluvial rivers. Today we will discuss more detail on suspended sediment concentrations. Going before that, again I want to highlight you that we have been following this book, okay, this very interesting book what we have been following it, and which has summarized the sediment transports in the rivers and quite well. That is the strength of this part, and as a river engineering, the components what we are interested on sediment transport part, that is what I am discussing on these classes. Looking that today what I will talk about, what are the equations are there to estimate the bed loads, which is quite interesting for us. Okay. What are the equations are there? There are so many types of equations are there. Then I will solve a simple example numerical problems to estimate bed shear stress. Then I will discuss about the vertical distributions of sediment concentrations. Okay. That is what in any river systems which depends upon a very interesting process which called turbulence boosting processes, and also we will discuss about analytical derivations. And then I will show it using this modeling concept of the flow and the sediment, okay, flow and the sediment transport process in a very complex river like Brahmaputra. We did a quasi steady simulations. That part also I will discuss. What are the equations available for bed load equations? Before that, let me tell it that the same slides what I used in the last class, just to repeat it, the data mining concept, data science concept what you were talking today, in as a river engineering we used this concept almost 70 years back, 1950. Okay. So, we try to write equations using 1950s for deriving equations. How did we do it? We follow the data mining techniques. We follow the data mining techniques. We have very lot of algorithms, but basic our objectives to establish the relationship flow variables and bed sediment properties with a bed load or incipient motions, the suspended load or the flow resistance, which is a very complex process as I discussed earlier. Non-dimensions variables also introduced for doing this process, like the particles Reynolds numbers, shield numbers, relative toughness height. So many non-dimensional parameters also introduced by establishing these relationships what for the bed load estimations, suspended load estimations or the total load estimations. We try to use plume data, plume experiment data, the river survey data, and we identify the flow variable, the sediment variable, sediment bed stratifications. Then we try to establish presently we call the data mining concept, but that is the data analysis techniques what was followed it almost 70 years back, okay, just near to the Second World War. So, if you look at that, this concept is well designed almost 70 years back. So, I do not want to go individuals equations level to explaining you because this course is meant for river engineering, but I want to just highlight one of the study what we did it on the predictive capability of bed load equations using the plume data. Okay, that is what the papers in 2012. So, if you look at these papers what we did it, we consider the plume data and we have a series of bed load equations, and those equations we try to see that which equations performs well. So, flow characteristics like we consider the velocity, the flow depth, the bed slope, particle size distributions. Okay. There are the equations are empirical equations, it does not have any basic concept that there are the equations semi empiricals. the partly it's analytically derived and partly it's established as a relationship. So, that is we call the semi empirical formulas we use to estimate the bed load transport. Okay. So, basically we try to look it in that papers what is the predictability of the bed load equations, and we divide it in two parts, moderate bed load transport and intense bed load transports. Okay. We categorize into two groups, and if you look at the summary of the hydraulic properties, okay, the flow width, the depth, okay, width is varying from 0.69 to 2 meters, depth, we have the sediment concentrations, the bed loads properties, velocities and age and sediment concentrations and the Einstein constants. The same way if you look at intense bed load transport, also we have used the data set which is having the flow width, depth, mean sediment properties, the standard deviations, the bed slope, flow velocity, age, sediment concentrations, gram per meter cube, all we consider it to look at that how the bed load equations are having the predictive capacity for these plume data. Now, if you look at that part, what are the equations? There are so many equations are there on bed loads. If you look at that, that's very old 1936 okay, CLD equations which has if you look at these formulas, okay, basically is a shear stress based approach. The same way if you look at the methodologies based on the shear stress approaches are so many. Okay, there are certain assumptions is there like graph 98 is very simple equations, it's just depend upon theta and theta c. There is a shield parameters at the critical stress. So, based on that we can compute what will be the bed load. So, same way if you look at there are different models, different empirical equations, there are lengthy expressions, there are the expressions which is having this a simple power function, and there are certain assumptions is there. So, same way if you look at this energy slope approach, okay, there are the equations is established based on energy slope approach is Mayer-Proto formula is in 1934 or Mayer-Miller formula 1948. Still these two equations are widely used because it is a energy based concept, and more or less if you look at that equations follow is that. And there are the probabilistic approach is way back in 1950 by the Einsteins, junior Einsteins established that what will be the bed load equations if we follow the probabilistic concept. What we are not going much detail for that, but if you look at there are so many equations here as it is listed, the 17 equations. Okay, the 17 bed loads equations are there. The point is coming is that which one is better predictability. What we try to do it, all these equations we implement it and try to look it for the two category for moderate conditions and for the intense conditions. If you look at these moderate conditions of sediment concentrations, there are Ashmore 1988 paper, Wong and Parker 2006 the equations. So, both these if you look at the scatter plot between observed versus the calculated, observed versus the calculated, really it is quite interesting, and that is what is expected in a natural river systems. Any equations what you develop it or any plumes, you cannot have exactly the matching of the data. So, you will have the spreading of the data, and you can look it the mostly it is improving in terms of R squares, the error components, but if you look at the scatter plot for moderate conditions, because the data collected it has some errors as well as the equations what is established from that period, it depends upon that concept and whether it is a validity is there. So, looking all the uncertainty in observations and model formulations, it is expected that this type of scatter plot could be there. Okay. But we are so similar way if you look it for intense conditions. Okay, it is quite interesting because that data is quite well spread. Okay, this is the varying from 0.00 to 0.40, and this is what is going up to 280. So, as the data spreading is there, And if you look at this Julian 2002 or Grabs which 1987s, both the observed and predictabilities are quite well. So, what I am to summarize based on this study is that instead of using the one equations, try to use the 2 or 3 equations, recalculate the bed loads, and you take a judgments based that how accurate it is. And most probably I can say that a few measurements can be included, any bed load estimations, you can do a few measurements or literatures about that rivers if it is available, you can use that and try to validate which is appropriate bed load equations for the particular river reach what you are working on that. So, that is what my experience when we working with river modelings. Okay. Now, if you look at coming back to a example problems, it is a very simple example problems we have given it here. Basically the problem is it is an online irrigation canal, okay, having the D50 size, okay, is 0.3 mm, okay, trapezoidal cross sections, okay, this is quite easy problems, okay, and it has the dimensions here is 300 meters, and here you have the 1.5 horizontal to vertical slope, and the longitudinal slope of this channel S naught is 0.0035. Okay. So, this is the condition. What is that? Discharge is given to us. Okay. Discharge is given to us 1.5 meter cube per second, and the flow depth is given is as 0.8 meter. So, in these alluvial channels definitely there is a flow resistance because of bed forms and the grain resistance because of the particle size on this bed. So, okay, the particle size on this bed. So, that is regions you will have the resistance to estimate the shear stress due to the grain roughness, okay, whatever this D50 particles, that is what is giving a resistance to for us. Also from that also compute what will be the shear stress due to bed forms. So, the bed forms are there and the grain roughnesses are there. So, we will do a simple calculations, and this is the data is which is there. If you can look it, the same data is highlighted here. The first what we will do it that we need to compute the basic geometry properties like area of the channel cross sections being a trapezoidals, you can compute it this part which comes out to be 3.36 meter square. We can find out the wetted perimeters, we can find out the hydraulic radius which is a ratio between flow area and the wetted perimeters is a comes out to be 0.571 okay, meter. Next is coming it that grain roughness we always have established a relationship with the n value, Manning's n values, the roughness coefficients as a empirical relationship with D50. Okay, that is what is the empirical relationships which is called a Stickler formulas. Based on that we can compute the NS value which is come out to be 0.0122. Okay, that is what Manning's roughness coefficients due to the grains, due to the particle size distributions of D50 values. Now, since the discharge is given to us, the flow depth is given to us, hydraulic radius is known to us, and the bed slope is known to us. So, we can inversely can compute what will be the equivalent Manning's n coefficients. That what we can do it. So, since all the data is given to us, so we can compute the n value which is considered the both the effect. This is a resistance due to the grain, also resistance due to the bed forms. That is what shear stress due to the grains we can establish, use these equations as a proportionate with a ratio between NS. The NS is the Manning's roughness coefficient based on the Stickler's equations, N is total roughness, what you get it. Based on that, if you just substitute these values, we will find the shear stress because of the grain roughness is this part. Since the flow, all these values are given it for omega r s naught, which is the shear stress. So, we can find out the total shear stress. So, this is the shear stress due to the grain. This is the shear stress due to total shear stress. So, subtracting these two, we should get it the shear stress due to the bed forms. That is what is coming about to this part. So, these are very simple examples, numerical examples we have discussed with you. Let us come with to very interesting topic on suspended sediment transport mechanisms. Here I am not going details, but still try to understand it. Suspended sediment concentrations, what it happens in the river is the primarily due to the turbulent structures. So, let me have a very good understanding that what it actually happens it. Like if you have the rough beds, okay, you have the rough beds, okay, some bed materials grains are theirs, and if you have the bed material grains are theirs, and when the flow is going through this, you cannot see it, but you can visualize that what will be formed this the turbulence vortices like this, okay. It is starting a formations of very micro scales, the turbulence eddies, the formations will vortices formations will be that. That is what slowly will grow it, further it is growing. It is in a 3-dimensional forms with the vortex change, okay. If you can see that vortex exchanges are there, and as is going through this surface to this, it grows it. Okay, the eddies formation grow it. Then at this point, the burstings happens it. At this point, the bursting happens it. So, if you look at the micro scales, this type of the process happens within the river, within the flow systems, and the very micro scales properties. If you look at that, that is what it happens the vortices, and these vortices. After certain stage, it cannot sustain this slope, it is bursting out, okay. And this bursting process exchange try to keep the sediment particles in the floating conditions. That is what it additional momentums because of this bursting process is what it happens it. Again it is the follow after the bursting side. If you look at that, very interesting, if you look at the velocity distribution up to these points, where it just formations of vortices are there, velocity distributions are not different. But as we go off, the lifting off, that at this point the sediment particles will lift it from the bed, then it will go for ejection process and the bursting process. And if you just look at the velocity distributions, how it is changing it, okay, like during the bursting process, the velocity distribution like this. During the ejection process, velocity distribution, and during the lifting process like this. After that, again velocity will come there. So, if you look at the macro scales of the process, what is happening it in a river flow, in a plumes, where you can really the process of turbulence burstings, the 70% of turbulence in open channel for because of the bursting process. These are the studies as for what is now in this decade has been going on. So, we are not going to that level of the particles levels to try to look at how the turbulence bursting phenomena is supporting the additional forces in the upward directions, and that is what is keeping the sediment particles, the lifting off, injected it, and it is remaining in the suspended stage. And if you look at how the process are happening, it is very interesting. Like this first phenomena, the sediment particles are lifted from the bed. Okay, the sediment particles will be lifted from the bed. That is what the sediment in the near bed regions picked up and lifted by the upward moving low speed band of the flow. Okay, the low speed is near the bed is a very low speed. That is what will happen. Then the highest positions of is reached by the particles being lifted. The particles which the sediment particle is lifted up, it goes to the highest positions. Okay, that is what is happening. the sediment reaches its highest positions after the burst breaks off. Okay. This burst is taking up the sediment particles. Once it burst off, that is the highest locations where the sediment can be carried by the turbulent structures up to the burst. After that bursting happens is particles start falling. Okay. But particle entertained by the water bodies with a large momentum swept away. So, that is the reasons the flow in the longitudinal directions having the large momentum, and that is what is help us the particle to swept away. Some particles the fell into the near bed regions, again come back to near bed regions. As the high speed regions of the flow reaches the bed, it spread to both the direction in the z direction, carry sediment into neighbor low speed regions. That the process can continue to happen, it is okay. This is the process can continuously happening it. Other particles will be lifted again before entering to the near bed regions. Sediment falls into another eddy and moving upwards. So, if you look at the very interestingly microscopically tracking the feed sediment particles, how it is suspended, how it falls down, how these further eddies are generated from near bed regions to the suspension regions, how it is reaches to the maxima reaches, all it depends upon the turbulent bursting phenomena. Okay. This is the process what we have been added, is that the same concept you can talk about how the process happens in aerosol movements in air or pollution movement in the air. So, the same process is happens it. So, if you are trying to look at that, when the water flow is there, there is a formation of the vortices, the turbulence vortices, as it grows it is having the bursting phenomena, and that is what is a control how the sediment mixings are happening it. So, river bed and the water zones. Most of the times what we look at, we do not have to go into more details how it happens at the particles levels. We try to look at what could be the particles distributions. That means, we know very well as this is the bed, okay, and it is a free surface. Okay. The sediment concentrations follows like this. Okay. This is the and this is the bed zone. This is the bed level. Sediment concentrations we look at behavior like this. Okay. It is highest at the bed regions and becomes exponentially decay down till to the free surface. Okay. So, this is the flow depth. Now, if you try to understand it, we are not looking at non-equilibrium condition, because we are looking at the equilibrium conditions where the sediment concentration profile does not change it. The vertical distributions of sediment concentration does not change it. If it is the equilibrium is coming it. If that is the conditions, let me I take it this z locations. Okay, this is z distance from this free surface. Okay, what will happen? There will be a sediment flux coming down, and there is a sediment flux is going up. These should be equal each other. Then these profiles remains at the equilibrium concentration. So, the sediment fluxes what is at this surface is going down and the lifting up both should be the same. Going down, so it is very easy, you know the settling velocities, you can find out with the sediment concentration C S B, you can find out what will be the amount of sediment concentrations will fall down with a settling velocity, and this because of sediment concentration gradient is there. Okay. S B gradient is there, that gradients have the upward sediment flux per unit horizontal area, that is what we do it, is a proportional to the concentrations gradient. That is we define as a constant, as a proportional constant of epsilon y. We are going to discuss that. So, if you look at that, this is a very basic concept what any process is happening for the diffusion equations, that the flux is always proportional to the concentric gradient. That is a same concept, the amount of downward sediment flux per horizontal area, we can define it this. If you equate it, you get a very simple ordinary differential equations with having SB unknown. So, which we can get the analytical solutions, where SB is a sediment concentrations, epsilon y is indicating the sediment exchange coefficients. Okay. That will be the different for the different sediment components. So, if you look at the next part, if you get the analytical solutions of these equations, the ordinary differential equations, it is very easy. You will get a exponential decay functions. Okay. That means, you know this, the SBI is a reference concentrations of the suspension sediment above the bed level, and the SB value you can get it, and here it is showing it how the SB by SBA sediment concentrations by sediment concentrated at the bed level, that ratio how it is depends upon your these coefficients, and if it is a plot in logarithmic values, you will get this linear relationship between them. That is what it is showing it, and these are all observed data. These are all observed data using this the particle side sediment mixtures, the Rose sediment experiment with a uniform strains. The Rose did that experiment and quite establishes that the sediment concentration profiles, it depends upon and we can always establish this part. Later on the questions comes is how to get it these coefficients. The Len and Kalinski suggested that it could be expressed as Karman constant, okay, as a logarithmic formulas for the velocity distributions. It can define as a shear velocity, flow depth, and the von Karman constants. You can define it through these ones, which is measure simplified the process. Now, if you look at this way, if you substitute von constants is 0.4, so you will get it this moment exchange coefficients, which is not nearly a constant, but is a uniform positions in a space. Okay, it is a flow depth dependent, but for the turbulence flow, okay, the diffusion coefficients is equivalent to the momentum exchange coefficients. Okay, it can be related with the diffusion coefficients. Okay, it can be related as equivalent at the momentum exchange coefficients, and Newton's laws of viscosities in a turbulence gradient. If I flow it, it will be give is these equations. It is very easy equations. So, that means the momentum exchange coefficient is equal to the momentum exchange coefficients. Okay, sorry, sediment exchange coefficient is equal to the moment exchange coefficients for the turbulent flow for simplicity, and then you can also find out the shear stress distributions as a linear distributions, and the tau naught is a shear stress at the bed. It is a very simple things. Okay. So, just substituting these values, if you interestingly if you can see that we can use the logarithmic velocity profiles, which is earlier we have discussed a lot, that velocity distributions is a logarithmic, and using these expressions we can always compute it what will be the sediment exchange coefficients and also the momentum exchange coefficient in turbulence flow, and if you look at that you can get a new equations in terms of SV. Okay. And if you solve that equations, is a simple equations, you will get a relationship. Now, more details in terms of flow depth, it is a y is a positions and the a and the z values. Okay. And the z value, z is a non-dimensional parameters, again we are defining z is a non-dimensional parameters in terms of settling velocity and the shear velocity. Now, if you look at the distributions patterns, which is the graphicals, we can get the solutions like this. For the different z value, okay, which is a functions of von Karman constants, settling velocities and the shear velocity. The shear stress is acting on the bed, which is also controls the suspended loads. So, if you look at that that part with a low value of Z value, sediment concentrations more or less uniform. This is the vertical directions, more or less uniform, but as the Z is increasing it, okay, these are just analytical solutions. As Z is increasing, see that if you look at that, sediments concentration profiles will be changed. Okay. So, it depends upon your Z value, which is the ratio between settling velocities and the shear velocities. These components, if you look at, and it has a distributions like this, Z is 1, you will have a distribution like this. So, we can get a sediment concentration profiles, how if we know the Z values. Okay. One parameter is depends upon the particle size, another parameters it depends upon the turbulent structures. So, if you look at that, these figures indicates that the relative vertical distributions of the suspended load concentrations, the smaller value of the Z, it results in a more uniform sediment distributions, and the height of the suspensions is always a function of Z value. This is the height of suspensions if you look at. Okay. This height of suspensions also it depends upon how far it will be lifted, okay, maximum. Okay. And that's the height of the suspensions is also function of the Z. So, Z is a very critical. Z is indicating is that the ratio between settling velocity of the sediment particles and the shear velocities, that is what represented how the sediment concentrations vertical distributions will change it, okay, as we are changing the Z values, which is analytical solutions that. So, because when Z is very small, we will have a uniform sediment distributions, but when Z is more, you will have the very less the height of suspensions, and you will have a distributions like this. So, these are very interesting things. This can be used also used the same way the particles, the sand particles in the air, we can concept of is also same, but only this data will be the change. Before concluding is that one of the studies what we have recently did it for the Brahmaputra rivers, I want to just to share with that. That is what is a quasi unsteady flow and sediment simulations. Okay. So, quite interesting study we did it for the Brahmaputra rivers, and the quasi unsteady means in this case we are not running total unsteady thing, but we are making a strip of steadiness, like we have the hydrographs, we are not simulating for the hydrographs, we are a patch of the steady modeling we do it, make it a quasi unsteady state. More detail you can refer to Hacker's technical manuals, we are not going to more details. And this is the model has set up for 200 kilometer of Brahmaputra rivers with having a discharge of 30,000 to 70,000 meter cube per second if you look at the discharge range, and try to look at how the sediment concentrations profile are changing it, how the bed level changes as this flood wave passes through it. That is quite interesting. So, okay, that is the things we have to try to understand how did Brahmaputra rivers behaves during the flood periods. Now, if you look at these results, which is a part of the MTech thesis, okay, recently worked on this. First is if you look at that, this is a 200 kilometers longitudinal directions, okay, and you see that bed level change, quite interesting. And some of the locations bed level change can have a as high of 5 meters. Okay. This is the depositions part, this is the erosion part. This is the aggradations, this is the degradations. You can see the cyclic of aggradations and degradations process. Same way, you look at the sediment concentrations, which is varies from as close as 2000 milligram per liters, which is quite high. Okay. But if you look at the distributions, quite interesting, just to think it. The sediment concentrations also varies quite interestingly. That is what it makes it the river is quite challenging to try to understand how the sediment concentrations vary from locations to location, how the bed degradation aggradations happens. Anyway, this is a theoretical data set, how these functions happens it. And if you try to look at, which we more interested to look at the velocity distributions, during this early flood the velocity can go as high of 6 meter per second, okay, it is quite high. But after the receding the floods, okay, you can have the discharge, the velocities will be on average of 2 meter per second. Okay. So, these are quite interesting, and that is the idea to share with you. Apart from having the analytical knowledge, use of the river modeling tools like HACRS and all, it also expands our knowledge on the rivers. So, with this I conclude today's lectures, that we discuss more details, that there are different type of bed load equations are there, and the shear stress approach gives a better result for that plume studies, but I do not want to tell it that this equation is best for that. That is the reasons as a river engineering we have to find out, take a number of bed load equation, test it and find out which is appropriate. I cannot say the best equations, I can say appropriate equations to estimate the bed load, and more often I can suggest it to have some sample data or the theoretical data, literature data to validate what the bed loads you are estimating it. Suspended sediment concentrations, as the last in these centuries we have been talking about turbulence, roasting process, and the jet, the vertical distributions of it also depends upon jet, which is the functions of settling velocity and the shear velocity. And we also giving a very interesting examples conducting a HACRS models, quasi unsteady flood sediment to show this how the fluvial process happening. With this I wish to conclude these lectures and sediment transports in rivers. Let me conclude these lectures by quoting a very interesting quote, is that the water is most critical resource issue of our lifetime, our children's lifetime. The health of our water is a principal measure of how we live on the land. That is what by Lona Leopold. So, what I am to tell it before concluding these lectures, that I just visited Japan from north to south. I have seen this water quality, okay, of all these rivers what if they have, and that water qualities indicates the life of the Japanese peoples. If you look at them, many are they cross more than 100 years life. That is what is my objectives to study the river engineering. Look our rivers, it is not a water flowing body. Thank you much.